this second chapter of trigonometry, we were going to be extending our knowledge of the trig functions. In this lesson, we will be introducing some simple trigonometric identities.
Okay, so we're going to start by looking at, as we said, trigonometric identities, okay, the first lesson here. Now, this is a new idea, okay, and an important idea in this trigonometry chapter here. We're going to start with identifying what we mean when we say identity. Okay. So what we mean by that is it's a statement that's true for all permissible values of the variable, okay, in the expression, and basically it makes both sides equal. Okay, so we're looking at something that's always true, no matter what you plug in. As long as that's a permissible value, when you plug it into the independent variable, both sides are the same, it's always an identity. So for example, the fact that tangent can be expressed as the sine of x over the cosine of x. So the tangent of x is the sine of x over cosine of x. That's basically almost true by definition. That's what tangent is. This is an identity. Tangent can be replaced with this. Sine over cos can be replaced with tangent. They are basically the same thing. That's an identity. Okay. Now you can demonstrate this graphically on the calculator by simply graphing both sides, and you would look and you notice you get the same graph. Now sometimes that's not quite telling enough. What I mean by that is, like, if I were to go to my calculator right now, and I'll do this right now, and I'll type in sine of x divided by the cosine of x. Okay, and then over here I'll put the tangent of x. Okay, and I'll just make sure that I'm in the, see what mode I'm in radians here. So this is probably good enough here. I'll graph that. There's my first graph. It's going, it's going, it's going. It's going, it's going, well done. So this is what sine of x divided by cosine of x looks like. Now notice it's still plotting graphs, but I'm not seeing any change here. So now that tells me one of two things. Either this is the exact same graph, and that's why I don't see any change, or it could be the case that actually it's not the same graph, but the new graph, the tangent of x, is not visible on that window screen. So another thing that you might do here, just to verify that they are identical, is to press second and then graph to get to my table of values. And what I'm looking to do here is to just verify that, yeah, those are all the exact same numbers. So for any input that I plug in, I am getting the exact same output there. They are the same, okay? They are one and the same. Now there are other identities, and you've seen these along the way here. X plus 1 squared is equal to x squared plus 2x plus 1. They are the same expression. One is just fact and the other one isn't. That's an identity. However, this right here, 2x minus 12 equals 8, that's not an identity, that's an equation. It's only true if x is equal to 10. Okay? And so if an expression can only be true at a specific value, not an identity. Okay, now with that in mind, let's take a look at some identities that you are already sort of familiar with at this point here. We've got what we call our reciprocal identities. Cosecant is 1 over sine. Secant is 1 over cos. Cotangent is 1 over tangent. Our quotient identities, and we've already seen one, tangent is sine over cos. Cotangent is cos over sine. Okay? So those are things that we should be familiar with at this point here. We're now just calling them identities. We're going to move on a little bit more here, because when we start talking about identities, one of the first things we're going to have to refer to here are restrictions on the variables. Now remember that when we talk about restrictions on the variables, we're stating that the denominator can't equal 0. Okay? So if I've got a times b in the denominator, then neither a nor b can be 0. If I've got a polynomial expression in the denominator, like 1 over x plus 1, well then x plus 1 can't be 0, and if I bring the 1 over, that means specifically for x can't be negative 1. Okay? Now, when we're dealing with trig, there's no difference there, okay? We are not allowed to have the denominator go to 0. Now, having said that, let's go up here. Would you look at that? Cosecant has a denominator. Secant has a denominator. Cotangent has a denominator. Tangent has a denominator, and I've already said this. Cotangent can be looked at as having 2 different denominators. Okay? These things have non-permissible values as a result. So that's what this is all about here. Okay? If an identity contains tangent, cotangent, secant, or cosecant anywhere in the identity, then there's going to be some undefined values here, because each of those has in itself a denominator. So here's an example right here. Tangent or secant, okay, because in both cases here, cosine's in the denominator. Since both denominators are cosine x, they have restrictions when cosine goes to 0. And cosine goes to 0, if you think about where cosine goes to 0, it's related to the x-coordinate. That's going to be anytime you get a terminal arm on the y-axis. So that's going to correspond to pi over 2, and then if you add pi to it, pi to it, pi to it, you're always going to bounce back and forth along the y-axis here. So here are my restrictions that automatically pop out if I see a tangent or a secant in the problem. Similarly, for cotangent, cosecant, they both have sine in the denominator, and so they're going to have restrictions when sine goes to 0. And now remember, think about the unit circle where sine goes to 0. Sine is associated with the y-coordinate, so it's going to go to 0, okay, when the terminal arm of the angle lies on the x-axis. And that's going to correspond to multiples of pi. So here's pi, and if I add pi, I'm back to the positive x-axis, add pi again, I'm over here. You just keep going around, okay? Now, that's if those guys show up anywhere in the expression here. However, there's one other thing you got to look for here. If an identity contains a denominator, then I got to look at where that denominator itself goes to 0, okay? So, first of all, I got to look at these particular functions right here, the tan, cotangent, secant, cosecant, and then I got to look at the denominator just like I would have done in previous courses to find those non-permissibles.
Determine the restrictions on the variable x in radians for each of the following expressions. The tangent of x.
Okay, well, for tangent, we already know that tangent, okay, is sine of x over cosine of x. Now, there's a couple ways you can go about doing this. One way, honestly, is to quite simply just remember that tangent has issues at on the y-axis. Okay, when cosine goes to 0 on the y-axis, and so you can kind of just pull this out here and just say, well, that's going to be where x is equal to pi over 2 plus n pi, where n is an element of the integers. Okay, so starting on the positive y-axis here, and then I go 180 down, there's a problem, 180 up, there's a problem, and so on. You could set cosine equal to 0 and then solve for that and get the general form here, but we just talked about this a couple minutes ago. That's the expression. So the issue here is just identifying the tangent has the cosine in the denominator, and when that happens, that's your restriction.
The sine of x plus 1 divided by the sine of x.
In this case here, notice that the expression has a sine in the denominator. Sine by itself does not have a restriction. So what I'm looking for here is when sine of x is equal to 0. Okay? So, and I have to state that I can't allow that to happen, right? We don't want that to happen here. Now, think about the unit circle. Sine is associated with the y-coordinate. Okay? So where along the unit circle does the y-coordinate go to 0? Well, y goes to 0 on the x-axis. That makes it an x-intercept. So any angle that I have, anytime the coterminal angle is on the x-axis, that will be a restriction here. So that means x cannot be allowed to be multiples of pi, okay, where n is an element of the integers. Okay. If I started at pi there, add a pi, subtract a pi, I'm always going to be back onto that x-axis. Can't allow that to happen. There's my restriction.
The tangent of x divided by 1 minus the cosine of x.
Okay, now this question here is going to have a couple of restrictions. First of all, a tangent shows up. So by default, I know that x cannot be allowed to be pi over 2 plus n pi, where n is an element of the integers. Okay, that's a restriction that comes from just the tangent all on its own. But in addition here, I've got a 1 minus cos in the denominator, and I got to deal with that. 1 minus cosine of x cannot be allowed to be equal to 0, which means, okay, I'll bring the 1 over and then divide by the negative. Cosine of x cannot be allowed to be equal to positive 1. Now, well, where does that occur? Okay, well, the cosine, remember, is related to the x-coordinate. So if we just think about the unit circle, along the unit circle, where does the x-coordinate, where could it possibly go to 1, positive 1? Well, right here. In fact, it's just on the positive x-axis. That's the only place where the cosine goes to 1. Now, what angle is that? Well, it's 0 degrees. Or, we're going up not even by fractions here, we're going up by full, okay, a full revolution here. So x cannot be allowed to be basically really 0, okay? But it can't be equal to multiples of 2 pi, where n is an element of the integers, okay? So going around the full circle, can't do that. Go backwards, can't do that. As long as you end up on that positive x-axis, that's not allowed. So there's my restriction, and here's the other part of it.
The cosecant of x divided by 1 minus the sine squared of x.
All right, well now this one has a cosecant in it. Now we know, or we should know, cosecant has that sign in the denominator, and remember there were two functions there, cotangent and cosecant, both had that sign in the denominator, and so the restriction that goes with that, okay, we can't allow x to equal multiples of pi. So x cannot equal n times pi, where n is an element of the integers. Can't do that. Now, I have another restriction though. I can't allow 1 minus the sine squared of x to be equal to 0. Can't let that happen. So I'm going to bring the sine squared over. So 1 cannot be allowed to be equal to the sine squared of x. Take the square root, and remember that that introduces some ambiguity here. I don't know whether we meant positive 1 or the negative 1. Now, I can't allow sine now to equal positive or negative 1. Now, where does that occur? Well, let's think about the unit circle. Sine should be associated with the y-coordinate. So where does that occur? Where does sine go to positive 1? Well, the y-coordinate goes to positive 1 here. It goes to negative 1 here. So it looks like I can't allow x to be equal to pi over 2 or 3 pi over 2. Now, those differ by pi radians, so I can actually kind of make this a little quicker to write here. I'm simply going to state that x cannot equal to pi over 2 plus n pi, where n is an element of the integers. And so I've got the two different sets of restrictions here. Now, this is similar to what happens when a cosine is in the denominator. We're going to talk about why that's the case in just a little bit here, but that's what I'm getting because of the ambiguity. I don't know whether I mean the positive or the negative, so I have to deal with both.
The tangent of x plus 1 divided by the tangent of x.
Okay, so this one here has a tangent in it, so immediately I can state that x cannot equal pi over 2 plus n, whoops, sorry, I was going to say 2 pi, but n pi, where n is an element of the integers. But it's also got a tangent in the denominator, which means I cannot allow tangent to equal 0 as well. Now let's think about that. Tangent, when you're going around the unit circle here, tangent is equal to the y-coordinate divided by the x-coordinate. So the tangent of theta is y over x. Now, I cannot allow this ratio here to become 0. Well, the only way that that ratio could be 0 is if the numerator goes to 0. If x goes to 0, then the thing becomes undefined, which is different. So really, I can't allow y to go to 0. Now, along the unit circle, where does that occur? That occurs here and here on the x-axis. So what this means is I cannot allow my angle to be multiples of pi. Okay? So I can't allow it to be either 0 or pi or 2 pi or 3 pi or going negatively around. That's why we use the integers there, right? So here are my two restrictions. I can't let x be equal to pi over 2 plus n pi, but I also can't let x equal multiples of pi. And that's because, this one is because tangent just shows up, period. And this one comes from that tan being in the denominator.
The sine of theta divided by the cosine of theta plus 1.
Right, now this one doesn't really suffer from any of the problems having a secant, cosecant, cotangent, tangent in there. So sine and cosine are not going to produce restrictions here. The only thing that I have to worry about here is I cannot allow cosine of theta plus 1 to be 0, which means I cannot allow the cosine of theta to be negative 1. Now, cosine, if you think about the unit circle, cosine is associated with the x-coordinate. So along the unit circle, where does cosine become negative 1? Well, the only spot that occurs is here on the negative, okay, part of the x-axis. And that gets associated with pi, okay? So I can't allow x to be equal to pi or any rotation that takes me to that negative x-axis there. So pi plus n 2 pi, where n is an element of the integers. I can't allow it to go around the circle starting there and ending there again. So those are the only restrictions that I get.
We will now look at a preliminary strategy for simplifying trigonometric expressions.
Okay, now before we get into the examples associated with this little description here, I just want to say one thing. When we talk about simplifying expressions, okay, we're trying to reduce them down as much as possible to get them to, again, the least number of trig functions that we can. Now, for the time being, based on where we're at right now, this method is really probably the quickest way to do it. Now, this is going to change, okay? This really works. I guess the best way to say this is for now. In a little while here, we're probably going to have to change this approach to adjust for new identities that you're going to see. But for the time being, we're going to convert everything to sine and cosine. If we've got fractions here, we're going to get a common denominator. We're adding fractions together. You can expand if necessary or factor if necessary. Now, these three here are what we might call obvious algebra. Okay? Oops, sorry, you can't see that. Obvious algebra. Either I'm working with fractions to combine them into one term. Sometimes you're going to see that, well, you're going to have to expand this to simplify it. Sometimes you're going to have to factor it to simplify it. Kind of depends on the problem. Now let's take a look at a few examples.
Simplify each expression. Cotangent of x multiplied by the sine of x.
Okay, to simplify this guy right here, we're going to first of all write it in terms of sine and cosine. Now notice cotangent is equivalent to cosine of x divided by the sine of x. And then this is now multiplied by the sine of x. Okay? Now I have done nothing. I haven't changed anything. This is identical to this because cotangent is cos divided by sine. Now, this is the same as sine over 1. Notice that I've got a sine in the numerator, sine in the denominator. So this is going to be equal to this will be the same as just my cosine of x. Okay? Now, normally when I did canceling here, I would want to spend some time discussing the non-permissibles, okay, the restrictions here, but that's not absolutely necessary right now. Actually, sorry, I should say that. This is identical to this. This is now simplified. Notice that cotangent here, this one has restrictions. Okay, cotangent has restrictions as long as x is not, oh shoot, just a quick little brain fart here. Sorry, that's embarrassing. N pi, where n is an element of the integers. Cosine doesn't have that restriction. So this expression would, this one doesn't. So to make them equal, I have to include reference to that restrictions.
The cotangent of x divided by the cosecant of x.
Okay, so for this one right here, we're going to write these in terms of sine and cosine. Cotangent is the same as cosine of x over the sine of x. Cosecant is the same as 1 divided by the sine of x. Okay, now in this case right here, I'm dividing fractions, so I'm going to multiply by the reciprocal. So the reciprocal of cosecant will just be sine. Now notice I get sine in the numerator and the denominator here, which means I can cancel those out. And I will get this is equal to cosine. But again, this original expression has restrictions. Okay, cotangent can't, cotangent has a denominator in it. So does cosecant. Now fortunately they're the same denominator, so they're going to produce the same restrictions. So this is only true so long as x is not equal to multiples of pi, written like that. Very similar to the one that we just did.
The tangent of x added to the secant of x.
Okay, so the first thing we're going to do is rewrite these. Tangent is sine of x over the cosine of x. They're identical to each other. And then secant is going to be 1 over the cosine of x. Notice that their denominators are the same. They're both cosines. So this is going to be the cosine of x. And I will simply write this as the sine of x plus 1. Okay, now there's really not much more I can do to this at this point. I can't simplify this any further. I can't really make this less. All I've done here is taken those two terms and made it a single term. Now in the previous questions, I had to identify non-permissibles because the result that I got, the expression all by itself, didn't have the same restrictions that the original had. And in identities, when you're working through them, they should be the same all the way down. They should be the same expressions here. So I have to include those restrictions. Here, each one of these has, this right here has the restriction that x cannot be equal to pi over 2 plus n pi, where n is an element of the integers. Okay, but you know what? So does the final answer. There is no change in the restrictions here because cosine is still in the denominator. So it's actually not absolutely necessary to write that unless you're asked for it, because these technically are absolutely the same. Over here, for example, this one is darn close to this one, except this also has to be stated because this has a restriction that this expression doesn't, so I have to include it to make them equal.
1 divided by the cotangent of x multiplied by the secant of x.
Okay, now there's a few different ways that we could approach this one, but to be consistent with what was written on the previous page here, what we'll do is we'll write these both as in terms of sine and cosine. Okay, so these are both in the denominator, so when I write them in terms of in terms of sine and cosine, I'll leave this in the denominator as well. So cotangent is cos over sine. Secant is 1 over cos. Now in this case right here, those cosines are going to cancel. I'm going to have to deal with that in a second here. Now what's going to happen here is I'm going to end up with 1 divided by 1 over the sine of x. And when I divide 1 divided by 1 over the sine of x, I multiply by the reciprocal. This is going to be the same as the sine of x. Now notice sine of x all by itself has no restrictions on it. But up here it does. Okay, there are restrictions here, so these are not the same unless you include those restrictions. Now, the restriction on cotangent, okay, x cannot equal, cotangent is going to be n pi, where n is an element of the integers. That's coming from the cotangent. Secant is going to have the restrictions that x cannot equal pi over 2. Pi over 2 plus n pi, where n is an element of the integers. Now I'm just going to double check that we've got them all. We can't let sine go to 0, can't let cosine go to 0, and so there they are. Those are the full restrictions right there.
1 minus the tangent of x, all divided by the cotangent of x minus 1.
Okay, so for this one right here, our first job is going to be to write these in terms of sine and cosine. So tangent is sine over cos, cotangent is cos over sine. Now, come over here. I've got fractions in the numerator, fractions in the denominator here. So what I'm going to have to do here is I'm going to have to find common denominator. So that becomes, in the numerator, this is going to become cosine of x minus the sine of x over the cosine of x. The denominator is going to be cosine of x minus the sine of x over the sine of x. Okay, so just got common denominators there, and then I put those two together. This is now the cosine of x minus the sine of x over the cosine of x times, and multiply by the reciprocal, the sine of x over the cosine of x minus the sine of x. Oh wow, we got this. Look, this is wonderful. That's going to cancel with that. And I'm going to be left with sine in the numerator over cosine in the denominator. And that's just equal to the tan of x. Okay, now, I have a tangent of x in here. I should really state some other restrictions here. And actually, I'm going to have to I'm going to run out of room here real quick. So I'm going to grab a sticky. Now, I can tell right away from here, from the original, because there's the presence of a tangent of x here, that x cannot equal pi over 2 plus n pi. But that tan stayed in the answer here. That is still there. So that's okay. Okay, I don't really even need to state that. I mean, it might be a good idea to say that x cannot equal pi over 2 plus n pi, where n is an element of the integers. That's not absolutely necessary because the tangent is still there. So that restriction is still there here. But notice that that cotangent disappeared. Cotangent carries with it the restriction that x cannot equal n pi, where n is an element of the integers. Now, because cotangent's now gone, that restriction seems to be vanished. but I need all of this to be the same, so I need to state that. Now, I've got one other little thing that I got to deal with. Okay, I need to look at the fact that cotangent of x minus 1, this is the denominator, I can't allow that to equal 0 either. So I got to bring that 1 over. So cotangent of x, I can't allow that to equal positive 1. Okay, but the nice thing about this is I know that cotangent is going to be positive in quadrants 1 and 3. I know that my reference angle here is going to be pi over 4. And I know that these things here are going to differ by pi. So I'm going to state here that x cannot equal pi over 4 plus n pi, where n is an element of the integers. Okay, I can't allow that to happen, because if that happens, then the denominator goes to 0. So I've got this one other restriction here, and I am running out of room to write it. I cannot allow, actually I'm going to do it like this. No, I really don't have room for that. So I will just have to tack this on at the end here. Sorry, this is way over here now. X cannot equal pi over 4 plus n pi, where n is an element of the integers. That's all coming from this one right here. So there's a lot of restrictions here.
The cosine squared of x minus the cosine of x minus 2, all divided by 6 times the cosine of x minus 12.
Okay, now this right here, notice everything's in terms of cosine already. But look at the way it's written here. I mean, just think about it. Look at it. Doesn't that you see the quadratic there? Doesn't that feel like you should factor that? Feels like that to me. So I'm going to do this right here. Cosine squared minus cos minus 2. Well, that really means this is going to be cos and this is going to be cos. Factors of 2 have got to be 2 and 1. Now I know this is pretty tight here, and one of them has to be negative inside there, one of them has to be positive. I want the cosine here to be negative, so this has got to be negative 2, positive 1. In the denominator, I'm going to get here that I can take out a common 6, and I'll be left with cosine of x minus 2. Those guys will cancel, so I'm going to be left with 1/6 times the cosine of x plus 1. Okay, now this is equal to this one right here, okay? Except for the fact that I canceled some stuff out here. Now, because I canceled that out here, I have to check this. This means that the cosine of x minus 2 cannot be allowed to equal 0, which means the cosine of x cannot be allowed to equal 2. Now, but wait a minute. Cosine never gets bigger than 1 and never gets less than negative 1. Cosine never does go to 2. So therefore, there's no restrictions here. That cannot happen, so there is no restriction on the expression.
We will now take a couple of moments to consider what it means to verify an identity.
Okay, so now we're going to move on and we're going to start looking at verifying identities. Now, let's see what it says here. When verifying an identity, we must treat the left side and the right side separately, okay, and work until both sides are equal. You can't move from one side to the other side of an identity. The ability to do that is only true. I guess it's predicated on the fact that both sides are equal. Essentially, when we're working with an identity, we don't know that that statement of equality is actually true. I'm trying to show that it's true. I'd like to believe that these two sides are equivalent to each other, but I don't know that. So before I get to that point, I cannot assume that they're true and just move stuff from one side to the other. That's only possible if this is a true statement here. So that's why you have to work on the left side and the right side independently. And when we do a verification, all we're doing is we're going to plug in an angle and just show that we can reduce the left side and the right side to the same numeric value. Now that doesn't prove that it's the same. All that does is show that for one angle, they are the same, okay? It doesn't prove that they're true for all angles. All I'm showing is that it works for one. What we're about to do here, these are not proofs.
Verify that pi over 6 satisfies cosecant of x is equal to cotangent of x divided by the cosine of x.
Okay, so what this means is we're going to take pi over 6 and we are going to plug that in. Now, we shouldn't actually say is a solution to. We're not really solving an equation. We're just showing that this is an identity, and so that this basically, we're going to verify that pi over 6 satisfies that expression. Okay, so now what we'll do here is we're going to plug in pi over 6. So this will be the cosecant of pi over 6. And this will be the cotangent of pi over 6 divided by the cosine of pi over 6. Okay, now, what is the cosecant of pi over 6? Okay, cosecant is the reciprocal of sine. So the sine of pi over 6, remember this is 30 degrees. Think back to your unit circle or to your special triangles or whatever you used. The sine of pi over 6 would be 1/2. So this is actually going to be equal to. Now come over here. Cotangent of pi over 6. Okay, cotangent of pi over 6. Now that's the reciprocal of tangent. So tangent of pi over 6, again, go to your unit circle. Tangent would have been 1 over root 3. So cotangent is going to be root 3. The cosine of pi over 6, well, that's going to be just root 3 over 2. Now, this expression here is root 3 over 1 times, I'm dividing by a fraction, so I'm going to multiply by the reciprocal. The root 3's will cancel, and I'm simply left with 2. So notice that the left side and the right side independently reduce down to the same number. We verified it.
Consider the following identity. Secant of x plus the secant of x multiplied by the cosine of x is equal to 1 plus the secant of x. Show that the identity is true when x is equal to pi over 4.
Okay, this question is similar in spirit to the one that we just did, just worded a little differently. We're just going to show that when we plug in that pi over 4, that the left side and the right side are equal. So we're going to plug in the secant of pi over 4 plus the secant of pi over 4 times the cosine of pi over 4. And over here we're going to get 1 plus the secant of pi over 4. Now, okay, the secant of pi over 4. Okay, well, secant is the reciprocal of cosine. Cosine is going to be 1 over root 2. So the secant will be just root 2 over 1. Okay? Well, here it is again, secant of pi over 4. So we know it's going to be root 2. And cosine is 1 over root 2. Over on this side, this is going to equal 1 plus, and again, we've already established that we know that the secant of pi over 4 is root 2. So let's just take a quick look here. I've got this term all by itself. There's really not much I can do about that. But notice that the root 2 and the root 2 here cancel, and we're just left with, whoops, sorry, not equal to. This is going to be plus 1. And now remember, addition is commutative. Order doesn't matter, so root 2 plus 1 equals root 2 plus 1. I've shown independently that they're equal to each other, so that verifies, that number, that pi over 4 verifies this identity.